Shall we start, Pradeep sir?
Yeah. Video, we are starting with video or not?
So
No, sir.
Okay, sure. We can start.
A very good evening to all the panelists, a speaker for the session, the president of IS Shakti, an honorary member of IS Shakti, Professor Prem Krishna, and all others who have joined us for today's webinar on modeling the dynamics of tall buildings under winds from historical perspective to recent advances and beyond by Professor Ahsan Kareem. So we extend a very warm welcome on behalf of IS Shakti to all who are present here for today's lecture. Before we begin with the proceedings of today, I request the President IS Shakti, Professor R. Pradeep Kumar, who is a professor at IIIT Hyderabad and presently holding the position of Director CSRI, CBRI Roorkee, and also the President of IS Shakti, to please give the welcome address. Over to you, Professor Pradeep.
Thank you, Professor Shilpa. On behalf of entire IS Shakti family, I extend my warm welcome to Professor Ahsan Kareem, who kindly agreed to deliver this lecture on tall buildings, that is dynamics of tall buildings under wind loads. So IS Shakti is a professional society serving the needs of structural engineers. It's an apex body which is serving the needs of structural engineers. Now coming to today's topic, this tall building, the boom for tall building construction in the country has started like a decade back, and we are seeing so many tall buildings are coming up. And the topic, because since we all know that tall buildings are susceptible for wind loads and form, natural period, and wind hazards, all these things have to be considered. So today this lecture is very apt because it is going from historical perspectives to recent advances. So tall building, India has a specific code, a code on tall buildings, that is IS 16700. So we in India consider this building which is above 50 meters up to 250 meters. So code has given guidelines. That was the first edition. And like as our understanding increases, we'll definitely make a lot of advancements in that code. And in that regard, I hope that this lecture will be very helpful to our fellow members and all the people who are participating. And I encourage all the participants to participate actively and write your questions in question answers box for later discussion with the speaker. So over to you, Professor Shilpa.
Thank you, Professor Pradeep, for your opening remarks. So now we move further for today's proceeding, and I take this opportunity to invite Professor Prem Krishna, a person who does not need any introduction, a very smiling, a white-haired person who is always smiling, a legend in the field of wind engineering, ex-professor IIT Roorkee, and also the GC member of IS Shakti, to please take this opportunity to welcome and introduce the speaker for today. Over to you, Professor Krishna.
Thank you, Dr. Shilpa. Great pleasure for me. Of course, first of all, I'll join Dr. Pradeep Kumar and Dr. Shilpa Paul in welcoming all those who have logged in for the lecture today. And maybe they're also from different time zones, just like our speaker is speaking to us just past 8 o'clock in the morning. And we are here at about 5:30. It's also my personal pleasure to welcome Professor Ahsan Kareem, who has been a friend of long-standing, several decades, in fact, 40 years this year. And while I cherish that friendship, I also would like to say that he is a friend of Indian wind engineering. Whatever efforts we do in this country to develop wind engineering, Professor Kareem is always at our back to help us. And I would like to thank him for his time to agreeing to giving this lecture at a relatively early hour from where he's located in the US. But friends, you may have seen his brief CV, from which it is clear that he has a formidable one, and he is a prolific researcher. His work is well known internationally for the path-breaking studies that he has been carrying out, which cover a wide range of applications. It's not just wind engineering that he covers. And very aptly, he has an impressive array of recognitions and awards. You may have seen these on his CV, but I would like to take this opportunity to repeat that. We start with his US Presidential Young Investigator Award, the Theodore von Karman Medal, the James Cross Medal, Robert H. Scanlon Medal, Jack E. Cermak Medal, and State of the Art Award from the American Society of Civil Engineers, and a very prestigious medal again in the area of wind engineering, that is the Allen G. Davenport Medal from the International Association of Wind Engineering. All these he has got for contributions to the dynamics of structures. Dr. Kareem was elected to the US National Academy of Engineering in 2009 and is a distinguished member of ACE. He is a fellow of the Indian National Academy of Engineering and has been president of International Association of Wind Engineering since 2015, which is 8 years. And during these 8 years, he has always been taking forward the agenda of the IAWE. As has been mentioned, Professor Kareem is going to talk to us today about wind effects on tall buildings, looking at the past, the present, and the future. I'm sure his critical analysis of the development so far and coverage of futuristic issues will be most enlightening. And those of us who are present and listening to him will pick up cues for future developmental work in this country as well, as it is very important for us. As mentioned by Dr. Pradeep Kumar, we are building now, increasingly we are building tall buildings. So this is a very aptly timed presentation that we are going to listen to. We talk of research at cutting edge. I'm sure Professor Kareem's presentation today will give us a peek into this cutting edge. With these few words, without standing between him and you who are looking forward to this presentation very keenly, I will request Professor Kareem to kindly make his presentation. Professor Kareem, over to you.
Thank you, Prem, and thank you, Pradeep and Shilpa, for the kind introduction. I met this smiling face also when I was also starting my career, and we met in Australia, and I saw this distinguished man, and I said, "Who are you?" So since that question, we became very close friends. I think it really blossomed in India, in Delhi, when he had chair of the International Conference on Wind Engineering at Ashoka and Samarat Hotel. And since then, we have always been very close. And I've always recognized Prem's leadership in India and worldwide in the area of wind engineering. I also was introduced by his book on cable structures. That's what was original. Once he told me in Australia, then I said, "Oh, he's that gentleman." Then, and another person I have always also interacted afterwards was Professor T.K. Datta, who has been also doing a lot of work on tall buildings and the dynamics end of things. Prem is more in the overall wind engineering. He has mostly focused on low-rise buildings. And you mentioned the Indian code. We did compare in one of our papers the Indian code as well, because my first visit to India was in Madras, Chennai now, was a CERC, Structural Engineering Research Center, where I visited twice. And in one time, I think Professor Davenport, Professor Vikri, and Professor Mehta, we were all together in that place where they had several, of course, Professor Krishna also arrived at that site. I think with this background, I think I'm going to just give you a little bit of a glimpse, especially to my younger listeners here. History is always very important, you know. You should always go a little bit of history because that gives you the right perspective of where this is coming from, and then you can decide which direction you want to take it. So I'll be giving you a little bit of history, a little bit about myself, why I'm talking about tall buildings, and then we'll slowly give you a glimpse of things, because I don't want to bore you on a Saturday, Friday afternoon with a lot of equations and too much details in wind engineering. So I will keep it more at the interface of structural engineering and wind engineering, and then see, you know, every place you touch these days is artificial intelligence. So I'll bring some of the applications into this particular field so that you can have a taste of that. So with this particular background, let's see if I can. Okay. Oh, no, gone too fast. Okay. So I came to the US to become a structural engineer, just like all of you do from that part of the world. And but I got interested into this motion of buildings. Tall buildings are moving, and I'll give you a little background later. But since then, I've been involved with, I did my PhD on tall buildings dynamics with Jack Cermak, and then was involved with a number of wind tunnel studies. Then I was actually the designer for the wind part for 2 of the tall buildings in Seattle. I've done sloshing dampers for various buildings around the world. And what, if you are familiar with ASCE E7, all the dynamics part is a part of our, contributions. I've been quite involved and interested in glass damage, and that has taken me around the world for that particular one. And we have also done full-scale monitoring of some of the very iconic buildings, including the Burj Khalifa, the world's tallest building. And I think as India is really coming up into the field of the tall buildings, I think some of my colleagues have been involved in some project in Bombay, Professor Kalaso and Ahmed from Samsung, who has been visiting India as part of the design firm. So with this background, I think what is the challenge I think we need to first look at? You know, on the top left, you see that we have, that's the origin of tall buildings in Bologna, Italy, where you know, they made these towers which look like tall buildings, and they are labeled as tall buildings, but they were not meant for people to live in them, but they were to have a better aim at your enemy, which is very sad start of tall buildings. But then Chicago had this iron developed, and we had the first tall buildings. At the same time, the elevators. So on the bottom left is the building in Chicago, which really led to the birth of tall building. Then we have been having a lot of, you know, Petronas Tower, Taipei 101, and Burj Khalifa. And now we are above the clouds. You know, if you're going in a plane, you might see some top portions of the tall buildings. And New York City is now coming back, and they are more into very slim buildings. You know, if you can see this building has an aspect ratio of 1:20, the top right one in Central Park, this particular building. And so the challenge is there. This is the tallest building in Europe. That's in St. Petersburg. This is, and they're building a second version of that one also. But Asia is taking a lead. And as I said, India is joining them now. This was a conference a few years ago in Shanghai, where I was one of the speakers, and the theme was Asia Ascending. And as you can see, all these buildings The tallest building is in sort of Asia. Then we have Madurka Tower, which is #2 buildings. This is in Kuala Lumpur now. And then comes Shanghai, and then comes our American building. But this is there because of this long spire. So there's a little technicality about the height of the tall building. Is it up to here or is it up to there? It all depends. Okay, so we always need to learn lessons from the past. If you look back, what we see is pagodas. I think Indian temples are not that tall, at least maybe I'm mistaken, one which I have visited, but in Japan and China, Korea, they are very tall. So basically, they are very good for natural disasters. Why they are good? Because look at the shape of the building, that just sort of disrupts the rhythm of the wind. So that wind cannot grasp the building to make it shake or whatever it wants to do. But if you look at the bottom, this is the structural engineering end of it. These guys were very smart. See, what they have is, they have these floors, and in the middle, they have this, just like we have tall buildings, we have core wall for elevator and other things. This one is called Shin Bashara. So what it does is that it serves as a spine for this building, and each floor can slide. So in an earthquake or a very strong wind, the floor can slide. That means these guys knew something about frictional dampers. Then if the structure moved too much, then there's a little hole. The floor might go and hit, like a snubber design for these machinery that goes and hits Shin Bashara. So there's the impact damper, which we all like to design these days. So these guys knew about friction dampers. They knew also the impact dampers. So at the same time, the top portion of the building was serving as a tune mass damper because they were tall. So on the right-hand side, I've shown some caricatures in which you got base isolation was there, slip joints, friction, and all things were built in. That's why those structures are still surviving and doing very well. And one of the guys who Cesar Pelli, I think, picked up for Petronas Tower, the same concept, the shape. And then once they went to Taipei 101, they very much similar to what you see over there. University of Tokyo used to have a building which is also like a pagoda, but unfortunately, this was my favorite building, and it has a liquid damper on the top of the building, but they dismantled it, and the different high-rise building is there. And if you carefully look at biomimicry, some of the wings of the birds also have reinforcements, which provide as a lesson of itself, a little different than what we have for pagodas. A little bit of what happens, when the wind hits a building. So let's look at this big globs or the ghosts. The turbulence have ghosts of different sizes. Once it comes and encounters a building like I have drawn here, they sort of hug the building, they turn around, they twist. So that's where the complicated mathematics happens. And as a result, this loads are introduced on structure, which we have to contend in. So as a result, as you can see, here's a building in Indianapolis where these intense wind events took care of the cladding, which is not very pleasant to be in that building at that time. But look at that Burj Khalifa. The world's tallest building does not have any damper. Why? Because they nip the evil in the bud. That's what is a British old word saying, that they shaped the building in such a way that you didn't have to worry about. As you can see, as you go from top to bottom, the shedding behind, or the whirlpools or the ghosts, have different patterns. So that means they cannot be synchronized. If you have a square building all the way to the top, they are very synchronized, and you're in trouble. Like that building in New York City has a humongous 2-floor damper to keep that in place. Otherwise, that would be just flying in the air. Then we have another issue is these days, I'm pretty sure India has the thunderstorm issue. We have always been designing things for boundary layer winds, we call them. As you design with your code, You might have 3 or 4 categories of the terrains over which you design the structure. But if you look at the response, this is actual response of the tallest building in Chicago. 2 different wind events. You can see irregular winds. This is a thunderstorm winds, and you see acceleration for a small time peaks up to 10. So we need to worry about stationary winds and non-synoptic winds. This brings back that Delhi conference. I think my paper was the second paper in the plenary session, opening plenary session, and I started giving the lesson of non-stationarity is important, and everybody sort of smiled at it. Oh, so it's Kareem is doing his stuff. Now you go to any wind conference, 70% of the papers are dealing with non-stationarity. So this is an area which we need to look carefully. Human biodynamic response to motion? You know, if you are sitting on the top floors of the building, things will vibrate. But it all started, even the early riders of chariots, they used to feel vibration problem. But those guys were tough. They just sort of ignored it. In early 70s, Wall Street Journal had this article, which changed my interest, brought my interest into the world, into tall buildings. They call it dizzy heights, because a building in Boston was moving too much that it was poorly designed. And so it was really dancing and people were getting sick. And that got a lot of notoriety. And then they eventually, I think about 10 years ago, put dampers in it. But basically that was a structural issue. So I did my master's thesis. Instead of doing on confinement of concrete and columns, I shifted. I said, oh, this biodynamic motion, a response to motion by human beings is another very interesting area. So I did my master's thesis in which I just looked at various features, psychological, physiological, and physical features, because every human being is different. Some people may like the motion of the building, other people may not like it. So I started looking at, coming from dynamics background, those of you, we have a transfer function always we use. If you are with a systems background, you will be talking about transfer function. If you are a structural dynamics type background, you will call it mechanical admittance function or something like that, What transfers load into response. So I thought that why can't we have a similar transfer function for a stimulus, which could be acceleration, and how we perceive, which would be reaction. And I came up with this stimulus is proportional to amplitude raised to the frequency power p, when normally p is 2, that gives us acceleration. So this is why people always look for acceleration for motion perception. So ASCE then had this wind-induced motion booklet. Those of you who are interested, there's a lot of background of how we perceive motion. And then those of you who are into performance-based design, I made this cartoon, which was very well received by the practicing engineers, but my academic guys sort of laughed at me. But I think this gives you how you react depending on what is the level of acceleration and how you perceive that. It conveyed a very good meaning on that. So what else can these winds do? Here is a collage of pictures in which we have had hurricanes and tornado. One of them is here, has caused damage to cladding. Even tall buildings, see all the cladding is gone. And it's not limited to US. It has also gone into Hong Kong, and India should watch out and learn from the lessons which we have learned. And this is New Orleans, as you can see, the whole Hyatt Regency Hotel is sort of affected by that. There is a very interesting thing for a structural engineering point of view happen. Let me bring you, this is the tallest, on the right, is the tallest building in Houston. Typically, the storm comes from this side and moves that way because Gulf of Mexico is somewhere on this side. Okay, so they designed this building, and they did wind tunnel study, but later on they decided to put this 12-story building annex, and that caused all the problems You can see it's in a Hurricane Ike, which passed through Houston. They look at the glass damage only on one face, and it is sort of around that building height. So we did a lot of investigation into that one because I was intrigued. The night the TV people were showing that there is a little tornado. This picture is taken from standing here, and the guy saw that there are little tornadoes in between the two buildings. Those tornadoes were not tornadoes, they are vortices, just like those ghosts I showed you. And they were causing to lift up glass and cause this breaking. This video is not working, but this is what they had noticed that. And as a result, you see this damage. So I call it saga of urban aerodynamics because we ignore this. This was never considered in any design practice, but then we can trace it back to what really happened, that one. Now, China is experiencing those things. This is Typhoon Mangkhut, and as you can see, the window panes are flying everywhere. The building on the right is a super tall building in Shenzhen, and I think that is moving up and down as well. So I think this is the lesson for India to keep in mind, because I'm sure you have a lot of debris like any other place, and debris gets lifted up, and it's not only the wind pressure which causes the damage, it's the impact of the debris which also becomes problem. So the cost of wind disasters is escalating, 665 billion in 2022. That's a lot of money to waste. We can feed a lot of people for that. So hazards cannot be eliminated, but we can engineer things to enhance their performance in these particular storms. I'm pretty sure you guys have cyclones. The Pacific Rim people have typhoon, and we have hurricane. And this year they're considering that it might be a very strong. But again, climate has some impact on these things, but those are cycles which keep on coming and going back. What do we do? Modeling the wind, and we come back. You know to tailor your structure, and we have 4 tools available to us: codes and practice, wind tunnel testing, full-scale monitoring, and this is the fastest emerging one, is the computational methods, which is becoming very popular. And I'm sure that a lot of people listening today are quite involved, because there are many papers I see from India talking about computational methods. Just to give you a history of tall buildings, in early 60s, they were thinking of making the 2 World Trade Center towers in New York City, which unfortunately are not there anymore. And these are some of the people who are involved with that. And I'll just focus on 3 people you probably might have heard. Some of you, Professor Davenport was mentioned when he was just starting his career. This is my advisor, Jack Cermak, in his wind tunnel, because he was the father of developing these boundary layers in the wind tunnel to scaling those things. And there they are. And the third person who was a structural designer is Les Robertson, who's sitting here. Oh, sorry, he's here. Okay, so this is the designer, and these 2 guys are helping him because he needed help. We never built a structure like that. And some of the architect was Yamazaki. And this is the New York City model then. If I have a today's picture, well, these buildings are not there, but everything is about this height around there, the new development. That comes as little few questions you have in the code. You see, originally, when they started this wind tunnel was in London, outside London. I think it is the National Physical Lab. That the wind tunnel is an aeronautical wind tunnel where you cannot develop a boundary layer. So they used to have a uniform velocity profile. So they did these World Trade Center towers, and they were getting 40 feet of deflection on the top. So there's something is wrong there. They added some turbulence that lowered down a little bit. They made this profile, which we use in the building codes, and put turbulence on it. Everything went down further. But now we have another challenge. That we have, this is the boundary layer in case of a thunderstorm. which is heavy at the bottom, where the other one is not. So the response changes accordingly. This is a proprietary picture. Please do not use it anywhere. This is from the World Trade Center towers. This is what they did in England, and they had response was way up. So the scale is sort of changed. So just to give you an idea that we come to the middle picture that is moderately rough boundary layer, and the right one is a boundary layer rough, and everything response to the building became to more reasonable value. So now we are flooded with wind tunnels. See all sorts of wind tunnels. I was part of the visit to Cirque in Chennai. Was the wind tunnel. They were just starting to develop, and we sort of participated in developing the profiles and high frequency force column. Lakshman and Selvi were the two persons there. We interacted with them, both at different ends of their career at that time. And China has some huge wind tunnels. US has built some very sophisticated wind tunnels recently. And another fashionable thing is now these multiple fan wind tunnels. And I assume that there's one in India, also probably somewhere in maybe Roorkee, or I'm not exactly sure. But India has one multiple fan wind tunnel. Now the question is also what we do with all these wind tunnels when the computational guys, the supercomputers are really crawling in, trying to compete with the wind tunnels. So just to give you, what do we do in the wind tunnel? Because a designer doesn't care what you do in the wind tunnel. He or she would like to have the loads acting on the building. A structural dynamicist would like to have more generalized loads on a building, mostly in the first mode. So how to measure them? See, in those days, pressure sensors were like $5,000 a piece. Today it is $50 or even cheaper. So people started thinking about load cells. But the trouble is the load cell has to be stiff and sensitive. See, two opposite type of requirements. Why stiff? Because they would like to see that the building when loaded on the shell, the frequency of the system is not less than 60 hertz. Because otherwise, instead of measuring the wind loads on the building, you will be polluting it with inertial loads. Earthquake guys are very familiar with inertial loads, because if my model starts moving, it is because of two reasons. One is the inertial loads and other is aerodynamic loads. But remember, my interest is only in the aerodynamic load because I cannot separate those. So then there's a various generations of these. Cermak was the original one in 1967, and the British guys came back. And I also started my thesis on a force balance, but then I decided there was a lot of engineer in me, and I said, developing this is more like a laboratory scientist job. I need to do something different. So in the middle, I gave up. I made one later and let other people do that. And I think the latest one we have is various version is this one in collaboration with my colleagues in Hong Kong. And this one has pressure sensors also on it. It can vibrate also. So it can do many more things than what the early versions which Cermak had in his mind. Then because as I said, the pressure sensors were very expensive. So we were using a lot of techniques to use minimum number of pressure transducers, but still measure area load. So what we were doing is we were measuring at various points, but we were averaging them in a little manifold. So this one output, but the input was like 20. So I did 20 sensors. This is primarily for loads, integral loads. If you are interested in a point pressure, then you cannot use this. So this was called local averaging. And I played with these to measure torsional loads, because if you weighting function is more on the end, smaller lever arm, you only put one pressure taps. So pneumatically, you are developing this torque on the structure. We also looked at distributed taps with triangular, and then also these PVD films came, which are sensitive to pressure. But unfortunately, you have to do a lot of work with them because they're also sensitive to temperature. And you don't know which one the reading is belonging to. So then there was a lot of development in this area. But today the world is that every wind tunnel laboratory, including some of yours, for example, at Roorkee and at other places, you have multiple pressure sensors, because the sensor is even less than $50 a piece, I think. And like mostly people have 600-700 pressure taps. So you can scan them simultaneously, so you don't have to do those things. But I'm giving you a history that if you don't have the tools, you are more innovative. We do these things. Today, a young person walks into the lab with 600 pressure sensors. All they have to connect, press the button, they're done. But this one needed a lot of ingenuity, which led to the current status where we are. So it's very helpful, because by doing this, I fully understood the anatomy of how the loads were developed. Today, when you do a press button and zip, everything is on the computer, you have no idea what happened on the building. But good thing is you have the results. This is one of the picture which is most widely used. You might have seen, anybody who has taken a wind engineering class, that we measure the force, we convert that into generalized wind load, we do modal analysis, we find building response. And here you can see the corresponding spectra. We normally work in frequency domain. So we have spectra of the wind, we got transfer functions of two kinds. This is aerodynamic, this is mechanical, to get the final response. I had an equation, I removed that, but I left one, because this is part of my PhD dissertation. When I was doing response of the building using these loads developed on the building, I realized that after certain wind speeds, I was not matching my measured response with a corresponding aeroelastic model of a building. And I realized, oh my God, when the building moves too much, it creates its own loads. So how to account for those? So at that time, I had some work done on bridges, and I sort of borrowed the concept from Flutter and brought in a coefficient J star in 1982 to compensate for the aerodynamic loads, which we also cause by negative aerodynamic damping. So now you can go to the journals. There are tons and tons of papers, people working on trying to find this J star, which I have that. While having accounted for that, my results match fine. As you have seen, the World Trade Center Tower have surrounding buildings. So this means if we didn't have these buildings, from every angle, the load on these towers is sort of symmetric. So the building doesn't have any torsional response. If you look at this cartoon here, here's a tall building. The wind is coming here, and it hits the front face. And this is the direction we call a long wind response. And 90 degrees to that is what we call a crosswind response. And obviously, we got torsional response. A crosswind response normally far exceeds the long wind response. But unfortunately, most of the building codes only address a long wind response, because we can compute that using this particular sequence of modules, which will give them And it's originally based on aircraft buffeting theory, but picked up by Professor Davenport for us, and he called it a loading chain. So, but if you put surrounding buildings, a symmetric section starts seeing some torsional loads, the torsion, because of the unsymmetry in the flow conditions. So this is one source of torsion. So you might not always assume that you have a square building and everything is very kosher. You don't have any problem, but the surroundings can create. Here is a Hyatt Regency in Tokyo. This building also have torsional issue because the building is unsymmetric, though the surroundings are not that bad. Then comes, structural dynamics 101. You got a building in which we have various centers. Shear center, you remember from strength of materials. Then you got geometric center, and you got aerodynamic center. So these centers do not coincide, you will have torsion. So I'm just alerting you guys. Nature is very good. Daffodils have a tendency, when the wind comes, they turn around and offer the wind the minimum drag. The wind goes away and they switch back. Unfortunately, we cannot do to the buildings, but later you might see some of the similar stuff. So in order to expedite this design process, we have developed computational platforms. So everybody doesn't have to be an expert in everything. So you can go to NatHas website. On the left-hand side, you'll see a lot of these tools which can help you to do design buildings, simulations, damping databases, virtual wind tunnel, CFD, damage assessment, and full-scale measurements. And here are some examples that you log into that. All you have to do is plug and play, and you will get your response. And even it includes the building codes from different countries, because every code has a different requirement. So you want to make sure that you don't design it for United States, but you design it for India or which other country you are involved with. So the game is played that we do this time history analysis. Here comes back that picture of the building with 600 pressure taps. We got to simulate that data, and that's all done on a web-enabled MATLAB code, which works behind the scene. The data doesn't have to come from wind tunnel. It can also come from CFD, computational fluid dynamics. There are papers which gives you more detail, and there are, I think I have to skip. Those people who are interested in occupancy comfort in tall buildings, we have not only provided how to compute response, but we've also provided some statistical analysis that how many people are going to be affected by this particular storm. So there are all sorts of webs available. We have now extended this to machine learning, in which with collaboration with our colleagues in China, we have come up with the left-hand side is our database, but it may not have everything. So what it does, it learns from what we have here to give us shapes which are a little bit closer to these shapes, but we don't have in the database. So here are some of the predictions, which are pretty good using machine learning and artificial intelligence. Building codes, as I've already talked about, is a very good solid way of doing things. And I've already gone through this wind loading chain. And I think I'm going to skip this little sketch. Building codes totally rely on equivalent static wind loads. And the dynamic loads are converted into a peak response. Either you can do full dynamic analysis, which everybody cannot afford, or you can develop an equivalent static wind load. Similar to earthquake engineering, where you got a base shear is equal to a long equation. Those who have done the wind analysis, the equivalent static wind load is the same way. And all the next step is, if you have the equivalent static load, you got to do the static analysis, not the dynamic analysis, and both will give you the peak response. So we will pause for a second. I need to get to my second half, which I'll try to go a little faster because things have been a little slow. Let me get my, yes, okay, I have to stop sharing. And oh. The two files are so big that I had to separate them because in this one, you see a lot of animations just to give you a glimpse of what computational tools can do. Okay, can you see my slide?
Yes.
Yes, sir. Yes.
Yes.
Yeah,
Yes, we
okay,
can.
now the second part, quickly, I'm going to go through computational wind engineering because that's the future. The fusion of CFD, stochastics, many of you do that, and machine learning and beyond. Everything, you know, is going digital. I don't have to make a case. And here's a recreation of Tacoma Narrows Bridge using computational fluid dynamics. Just like in a wind tunnel, this is my computational domain, and I'm studying the behavior of a square building. So we have to do the inflow conditions like we do in the wind tunnel. We need to look at the modeling of turbulence, how close near the building, how the mesh is going to be. And we want to capture all these things. So means to capture a very tiny one, the mesh size has to be very small. So we develop synthetic turbulence, and this is a field in itself. And here is some example of inflow conditions. We can also use not CPUs, but GPUs because that expedite the simulation process. If the building is moving, we can also accommodate that. And in this way, we got a coupled response between fluid and the structure. Here is an example that we took San Francisco, part of San Francisco, and got the database of all the buildings. From there, we created a mesh of the building, developed a CFD model, and once we got the loads, we coupled that with a structural dynamics model of the building to find the response of those. Here is some more computational details, which are not that important at this time. And here is the example. This is an exaggerated 100 times the building response. The left-hand side shows you the wind field at 20 meters. The advantage with CFD is that you can find this flow field at any level. In the wind tunnel, you can measure at most 6, 7 points, 10 points, 20 points at one level only. But here you can measure it in different levels. You can see those dancing buildings, but that's 100 times. We have then compared them to the wind tunnel measurements. The mean do very good. RMS does very good. We have some issues with the peak response, which needs further refinement. So we can give the designers a chart like that, that the buildings which are red, they need to worry about. By the way, this is San Francisco doesn't have that many buildings which are in red, but because we use a higher wind speed, just to see what things are, because San Francisco doesn't have too many tall buildings. It will be different in New York City. Also, we can give pedestrian comfort. We tell them, hey, these are the red spots. You got to worry about it. See a different percentage of people who will be objecting to that. So this is a very powerful tool for the design office to be using. we have another issue we found out in China. One of the building on a not a very windy day started vibrating in Shenzhen on 2 years ago. And you can see the spires on the top was also moving and everything. So first thing we want to know, we wanted to analyze it. We need to know what is the wind speed there. We didn't have much measurements. So these are the measurements of the mast. Now, again, we had access to the accelerometer data, but we are not supposed to publish that. So we use another way. We had a video taken of the thing from the street, which nobody has a right to that. Anybody can take a video. So using vision-based analysis, we have done these spectra of the response and the time history of response, which is a very clever way to handle these things. Then we went into our CFD simulation of a storm, large scale, kept on bringing it to a shorter area. And we eventually got to the boundary layer near the building. And then we started modeling the building around. And these are the flow around that building in various parts of the structure. Oops. And as a result, we found out that, the mean wind speed there was sufficient to cause the masts of the building go into vibration due to vortex shedding. And then, like they say, tail wagging the dog. That's one of the British thing. It's the same thing. The tail on the top of the building was actually wagging the building. So building was not vibrating because of wind, but the wind vibrated the towers, the spires, and the spires shook up the building. See, this is another problem. One of the reasons we have damping, we need to put damping in sloshing dampers and tune mass dampers, because if we don't do that, when the structure stops vibrating due to earthquake, the tune mass damper mass will be still moving and it will become a shaker. So that's why we put damping in the secondary system, so that after the event is over, that mass needs to calm down also. Otherwise, it becomes the same as this particular building. These are some other things, working with a colleague, Professor Hu, in HIT Shenzhen, where he is using a lot of physics-informed graph-assisted autoencoder, where these are the city map, where we have some measurements like 5-6 places. Like in Bombay or Delhi, you have, say, 10 sensors. You want to find out what is happening around the city. Now there are tools available, and this was one example. And as you see, the top row is for predictions. The bottom one is the ground truth, because Japanese had done a lot of measurements. This is part of a city in Tokyo where we use their data, try to benchmark this particular method. So a lot of new things are coming. We can predict, you can measure, this is the ground truth, this is the prediction of pressure fluctuation in the building. Say you can only run for 30 seconds, and then you can create 1 hour using machine learning. And this is one example of that particular. We are developing a virtual twin or digital twin of a wind tunnel at University of Florida. So you can do on your computer, before you go for doing your experiment, you can do everything on your virtual wind tunnel. So that way you can design your experiment better, do some validations. The rest is all the story. Many of you are very familiar with the digital twins, or have made them also. So I won't go into the details. I forgot, so far, I said I have a global living laboratory, or used to have it, where we have 3 buildings in Chicago, Boston, Dubai, and in Seoul, Korea, where we had done some very sophisticated work, especially monitoring this, very tall, 800-meter tall building. You can't run a cable from there to down there. That will make you bankrupt. Not only, even if you have the money, nobody is going to let you pass their cable through their bedroom closet when they are paid like $20 million for a condo. So we had to come up with this very smart way of, which I call it real-time system identification, and we use smart sync concept. Later on, we found that people call it Internet of Things. We were before theirs, but this is actually an Internet of Things, where each sensor is dumped into the internet right at its location. So we don't use cable, virtual cables. Then the computer at the base of the building does all the work. And then we can go from internet to wherever we want to go. And we also did some calculations at the site, at the sensor, which is now called as edge computing, because you distribute it, you don't do everything at the central process. So this is for the first time in a real building where you can sit down and see how damping is changing from fraction of a second, how frequency is changing, how the mode shapes are, which are been done. So anybody interested, you can remember Smart Sync and Google it, and you'll get the paper where we're going. I don't have time for this, my dynamic shaker, but this is something which I'm very proud of. It's a very simple thing. You know, we have sophisticated methods for system identification, and I'm pretty sure that some people in the audience are experts in some of those methods. We have come up with something I call a virtual dynamic shaker, which is based on Dynamics 101. Half an hour lecture on dynamics, and you are good to go. And you compete 100% with most sophisticated methods. What I was trying to reproduce was, as Prem probably knows, the work done at Caltech and BRE, they had these huge shakers in Sheffield. They would take it to the top of the building and shake it up to get the damping and the frequency and the mode shapes, and we done that virtually. Here is my building. It is being excited by wind. Here is my response. I take this response and feed into a virtual damper, or you want to call it damper, a small mass, and I get response. I have a radio button where I can change the frequency on MATLAB of this K. The response would be like, the response of this guy would be here, here. When this frequency is the same as the building frequency, all of a sudden, zoop, and that is my system identification for the frequency of the building. Similar trick can be played with the damping. And I have compared here some full-scale data, some simulated data, and compared with some of the most sophisticated techniques available, ERA, NEXT, and all those people who are familiar with them, and see how close we are, or they are to our method, because we don't know, they are better or we are better. But we are very, very within few percentage points. So my question is, Professor Davenport always used to say simplicity, and I think Professor Prem Krishna also promoted that. Simplicity is very important. System identification, we got a huge field, we got so many complicated methods. Here is Dynamics 101, gives you results very similar to what you have in. We have developed also a web-enabled app for this, so that all you need to do is your response MATLAB time history, just paste it, you get all your results. We have done some other clustering analysis. I don't have time to get into the detail because we have so much data coming from Burj Khalifa. And if you're only interested in vibration of the pinnacle, you will have hundreds of people sitting looking at the data to find it. But machine learning sort of isolates it through clustering technique, so we can have only the vortex-induced vibration data for that building. Damping models we have done, sloshing dampers we have done for buildings and structures. We have done some hybrid testing of sloshing damper, because sloshing damper is a nonlinear system, so we have difficulty predicting it. So what you do is, like in earthquakes people do, whatever you cannot model, like a joint, you put it in real life, and the rest is on computer. So what we can do, this is what we want to do, this is what we partially want to do. Sometimes the swimming pools and the sloshing dampers can be bad. Just the same thing I told you, we have to dampen the motion. Unfortunately, you cannot do that for a swimming pool, but for dampers we can. This happens and can happen. We have been doing some work in shape optimization, and I won't go into details. We can change the marrying the form and the structure. That is structural engineering, where you can shape optimize, because shape, as you saw in case of Burj, really helps. Here is an example of one of the building in Ladakha Tower in Russia and St. Petersburg, where the building is twisting, bending, and it makes a very good case for reducing the loads on the building. And this is designed by Samsung Corporation. We are also looking into living facades. Why can't the building change the shape in real time? So we have developed some scheme which we copy the birds. And I don't have the time detail, but the living facades will be coming. Most of the people in the audience will be designing those in the next 10 years or 5 years. You can harvest energy from the buildings, which is also becoming popular. This is my last slide. In 73, my famous professor at MIT, Professor Hansen, he asked me, I had a project, and my conclusion of the project was, this is in the bold letters. People who occupy tall buildings need to be informed and conditioned to the performance of buildings during windstorms. And he thought I was crazy. This is a bad idea. We should design our buildings so that we don't have to do that. I don't think we have been succeeded in designing building that way, but we have been better in educating people. Dr. Les Robertson, many years ago, was staying in Hyatt Hotel in San Francisco. And in the drawer, he found this card. And he picked that up and put in the mailer and mailed it to me because I had told him about this story. So a few decades after that, Hyatt Regency is telling people the same thing. Don't worry, building is going to move. It will make some sounds, but you're okay. So with that note, I'm sorry for going a few minutes over, and I'll stop here. Sorry, I had packed up too much stuff, but I got into a little more details at the beginning because majority of the audience might be structural engineers only, and I wanted to make sure they don't get thrown off with too much of wind engineering jargon. So I wanted to explain that. So I'll pause here. Thank you very much again for inviting me with this very prestigious institution or association of structural engineers, which will shape the future built environment in India. Thank you.
Thanks very much, Ahsan. It's been a great lecture. I'm sure we all enjoyed it and learned a lot from it. As usual, there will be a few questions. I think Dr. Pradeep Kumar is going to.
Yeah, I'll take up these questions, sir. It was indeed a great lecture, sir. Great lecture. So, sir, you can remove the screen now. You can unshare the screen. Yeah. So there are a few questions in the question and answer box. So I'll be taking one by one. So the first question is by Dr. Abhay Gupta. He is asking, please enlighten us on the natural time period of buildings to be considered for dynamic wind analysis. So there is a basic difference between philosophy for wind and for earthquake analysis. So
that's the issue we had because ASCE 7, we got a chapter on earthquake engineering and a chapter on wind engineering. And we have guidance for damping and frequency in earthquake, and we have a similar one in wind. And they are in contradiction with each other because the design philosophy is different in both cases. So we want to make sure that the building resists earthquakes. And if you make them too stiff, they'll be more sensitive to wind, to earthquakes. If the building, you don't have in that issue, but the damping is a criteria. So this is a little bit of dichotomy we have. One has to make sure which particular zone we are designing your building, and you want to develop some happy balance between the two options. And also, another uncertainty you might feel, especially it happens with concrete buildings, that what you do by finite element analysis and what you measure is totally different. Sometimes 100% different. And especially when we are doing tune mass dampers or sloshing dampers, and you monitor, you design it based on the finite element code which the engineer provides them. That say may have a period of frequency of 0.2. When you do the building, you get, say, 0.3 actual built. Because the trouble is when you do finite element modeling of concrete building, you are difficult to assign the level of cracking, the level of participation of the partitions. So this is a big dilemma. I don't think it has been solved yet, but I think the designers sort of tweak things back and forth. Concrete building is a problem for us because we have monitored so many buildings. For steel building, we can come within a fraction of a percentage. Measured like Sears Tower in Chicago, we had almost 100% matched what the finite element code gave us and what we monitored. So this is a question which you have to carefully manage. If you are in earthquake zone, probably you don't have to worry about what the wind guys do. But if you're in a wind zone, normally wind is going to control. Even in San Francisco, many buildings are, the very super tall buildings have wind is more sensitivity, unless you are dealing with very higher modes. Professor Dr. Bonawakar from CVM Engineers, long time ago, gave a seminar at our place, and he said that this particular building was the tallest building in San Francisco, but the Houston guys got to design it. And they found that 65th mode was the first mode which was important for earthquake because the local joint was being overstressed. The rest was all controlled by wind. So I'm not saying which one should be designed for, but I think you should evaluate, and that will help you guide to the answer which the gentleman asked. Yeah.
Okay,
Thank you.
Thank you. Yeah, I'll go to the next question. This is by Pranesh. So at what height of a building wind loads become critical compared to earthquake loads? And what is the difference in their dynamics?
Again, this question may change from structural system to structural system, concrete building or a steel building. I think the ASCE 7 provides some guidelines. I can tell you off my head. There's certain frequency that tells you if you're below this, you got to, above this is okay, but below you have to do for wind. I think the best thing is that you, even in Iceland, there is a 5-story building which has a problem with wind because it's very windy there. So you have to see your environment you are in. These days, you have a finite element model of your building anyway. Every design firm has that. Just convert that into a single degree of freedom system and put some loads on it and see how it works. So you will find out very quickly whether wind is going to do design. Because these days, those thumb rules used to be good in our days where we don't have the resources. Now, while you're having coffee, you press button, you got everything done on computer. So my feeling is that rather than worrying about these thumb rules, if we go into just actual analysis and to make sure when in doubt, definitely a 5-story building is not going to be dominated by earthquake and not by wind. But once you go over 40 stories, I think you got to start worrying about wind quite a bit.
Thank you, sir. Yeah, the next question is by V. Rao. When the city is developing, what type of wind study to be done to be future safe?
That's a very interesting question. That's where the public policy comes into picture, because a developer is not interested in what happens to your building next doors. Right now, there is no law that if you are putting a building, what are you going to do to my building? Some cities are now coming up that once you do a new building, you have to do some study of how it is going to affect the surrounding building. Ideally, as the question was asked, one should study beforehand a overall grand scheme of things for that particular city, where I think the analysis, where you can put hypothetical buildings and start looking at the wind environment and see from there how you can go. But the trouble is, who is going to pay the bill? That's where the problem comes. City is not going to do it. The government is not going to do it. And as you can see, we have many things which can be resolved better if it is done by the policy, but the policy guys are only looking at what happens next year. They don't care what happens the year after. And I think it's uniform all over the world. So you will have the same challenge. But this is the right way to do is that you should do city planning, town planners to make sure that they can have a right balance of buildings and their orientation. I think this will help long ways in ventilation. City ventilation is important, and pollution is going to be important. And some cities are now looking at these effects, but probably not to the level which is the question has been asked.
Yes, sir. So I'll go to the next question by Bhargav Shashikant Rawal. So which type of dampers are most suitable for wind-sensitive tall building?
There are two types of broader category. If we are talking about passive dampers, that is the first category. And I would agree that we need to go to passive dampers because you don't have to do maintenance. Because this is not an aircraft or $1 billion building that somebody's going to have a maintenance guy. In a condo with a 40-story condo, I don't think they're going to have that many technical people involved with that. So passive dampers are more important. So in passive damper, there are two categories. One is inertial dampers, which is tune mass damper, and sloshing damper. Or we could have viscous dampers like shock absorbers in our car. So for wind-induced response, I think it's better to use an inertial system, which could be better it be a tuned sloshing damper, because the two which I have done, one in a tall building in Manila and one in Dallas, if the owner doesn't want it, they think the building is fine, they can drain it, bring the guy and they put, finish the room, and you can use that room on the top floor. If you have a damper like a tune mass damper, that is a little bit more expensive to install, has to be maintained a little bit, and to remove it, it's the same reverse cost again. So we are mostly doing a lot of, for concrete condos, the sloshing dampers are becoming very popular. By the way, I discovered the sloshing damper while I was playing with a building for earthquakes, and I had a swimming pool at the top floor. And this is like mid-80s. And we realized then when the swimming pool sloshing was tuned with the building, the response reduced. And then we had paper in Journal of Sound and Vibration in 1987. And at the same time, Professor Modi from Vancouver, British Columbia, was working in nutritional dampers like a donut for satellites, but we were both published in 1987 independently. He was more interested in aerospace structures, and I was with buildings. But I would recommend that first look into sloshing damper if that's not possible, because sometimes water is much lighter than lead, so you have to use a lot of water. So you have to look at the cost-benefit analysis, and you may consider the viscous dampers, but the building in wind is primarily dominated by the first mode. So you need somebody on the top to tell the building, hey, you're not going to go that way. If you go with those viscous dampers, they'll be distributed all over the building. That's more better for earthquakes because higher modes play a role. And there that acts like a snake and comes into action and works there. It's a good question, yes.
Sir, yeah, I think there are many questions, but I'll take up last two questions and then I'll hand it over to Professor Prem Krishna. Yeah, the next question is by Shetadru Bhattacharya. Vortex-induced vibration can be more predominant in case of building frequency less than 1 Hertz. How to determine like turbulent length scale to model wind environment with CDRFG technique?
I think if I understood the question right, there is a formula which design engineers should use it, that S equal to frequency multiplied by the width of the building divided by the wind speed. S is called screw-hole number, and it is tabulated in any book for different building shapes. Okay, so for square building is about 0.1. So you put 0.1, you know your frequency of the building, you know its width, and you know the wind velocity at which you will have vortex shedding. And this is the first thing people check, designer, and you want to make sure that you do something different to go away from that. For example, if you change the shape of the building along the height, you have totally messed this up and you're okay. But I'm sure that that option may not be available for a typical 20-story condo building because you have a certain budget and you want to do certain things on there. So, but you need to avoid this resonance with vortex shedding. I think that was the question. The length scale is another which I heard. I think there was a secondary refinements, icing on the cake, but this is what is the first check as a structural engineer.
Yes, sir. Thank you. So this is the last one I'll take up. So what is your view on performance of sloshing damper under seismic excitation?
They work, but the trouble is that, as you know, there are two types of earthquakes. One is a far field earthquake and one is a near field earthquake. Near field earthquake, one example is El Centro, which we have all studied in our structural dynamics class. That means right off the bat, you had sudden ground motion very quickly. Okay. So sloshing damper as well as tune mass damper are not effective because they're still sleeping and the biggest jolt has already arrived and they have not reacted and your structural system has suffered from it. So passive dampers are not good for those types of earthquakes. But if the area where your building is, like Chicago, and you're worried about earthquakes in Mexico, they are real far field earthquakes. They will make your building move. Or in Mexico City, you can have sloshing damper and will definitely help, but it will take a little time. The initial part of the earthquake, you may suffer, and the latter part, it will become active enough to participate.
Yep. Thank you, sir. There are some more questions, but what?
And they're welcome to email me. Yeah, my email,
exactly.
my last name at nd, like Notre Dame.edu. Very simple.
Sure. Thank
I'll
you.
be happy to answer.
Thank you so much, sir. Now I'm handing it over to Professor Prem Krishna, sir, to sum up the workshop.
Yes, I wouldn't take long because after a lecture like that, you don't sum up.
That's true.
It's been such an enjoyable experience listening to you, Ahsan. You've taken us through the entire journey of tall building aerodynamics, the way things developed. And remarkably, the many things that you did broke new ground in this area of aerodynamics. But the final part, the most exciting part, is the way that you have, in a big way, shown us how to adopt the latest developments in artificial intelligence or machine learning, computer-based work. And this then holds a big promise of being able to look at problems of aerodynamics through computational methods of their application. Because at least till recently, people always thought that computational methods will give you answers, but you still you need to go back and prove them through testing of one kind or the other. So maybe we are looking at a situation where the developments that are taking place will make the testing part, which is onerous, to say the least. It's not the press button type of thing. It will be very, very nicely supplemented with the computational methods. So that's the exciting part, and the biggest takeaway that I have from your lecture today, and maybe other people who have listened to you. I'm very thankful to you, Ahsan, for finding the time for us and talking to us. And there are many things which you didn't have time to explain in detail. Maybe people will get back to you and will want to have more explanations about some of the developments later. Thank you.
Thank you. And I just want to close that many of you, all structural engineers, distinguished structural engineers, are gathered together. I'm not sure that you're aware that International Association for Wind Engineering, which I serve as a president, especially gave a special presidential award to 4 people, very senior people from Japan, US, and England. And the 4th person was Professor Prem Krishna. And we had a little ceremony. I think some of you joined, but many of you may not know about it. And this was a nice little ceremony we had. And it had a little plaque and a certificate. And we are very honored the torch which Professor Prem Krishna has carried not only in India, but internationally as well, because at one time he chaired the International Wind Engineering Conference in Delhi, which was very sweet place, because I still remember gulab jamuns in the Shoka Hotel. With that note, thank you very much for listening to me, and look forward to seeing you somewhere in person. Take care.
You, sir.
Yeah.
Bye.
Thank you.
Yeah. Thank you. Yeah.
Bye-bye.
Yeah. Thank you is, yeah. Yes. Thank you
Bye.
is such a prayer that cannot be seen or touched. It must be felt by heart. And it's my pleasure and a privilege to propose a vote of thanks for today's dynamic lecture on wind dynamics.
Thank you
On
very
behalf
much.
of ISTACTI, I would like to thank and express my gratitude to Professor Ahsan Kareem for a very informative lecture, and he has taken us from the history of the formation of the wind tunnel to human biodynamics, response to motion, to performance-based design, to computational fluid dynamics, to virtual wind tunnel, and many more. And as you have very rightly said, sir, hazards cannot be eliminated, but their impact can be minimized through the engineering resilience, but thus enhancing the engineering resilience. And thus we should all work with that focus. So thank you, sir, for a very, very informative lecture. I would also like to thank the panelists for today, Professor Prem Krishna, Professor R. Pradeep Kumar, for making the discussion very productive. And I think we have many takeaways from the today for all our participants. Any session of a webinar is not successful without the participants. And it is very good to see that we had 237 participants, and not only from India, but also from abroad, who were attending the lecture. And we are assured that Professor Kareem's lecture had cleared many points in the minds of our young engineers and has opened many areas in the minds of the engineers and the researchers to work upon, with the ocean of opportunities ahead to work in the field of wind engineering. I would also like to thank all the GC members and the members of ISTACTI for your participation in the today's lecture. Last but not the least, I would like to thank ISTACTI Secretariat for the smooth arrangement for the conduct of today's webinar. So looking forward to have all of you again for the other events by ISTACTI, which ISTACTI is working continuously for providing the knowledge sharing platform amongst our structural engineers. So wishing a very good evening to all of you and a good day to Professor Ahsan from all of us at ISTACTI. Thank you, sir, once again.
Bye.